In this video, I want to go over some problems that have to do with function transformations. I don't want to go into the details of the concepts because those can be found elsewhere. I just want to work a couple problems and go through some basics. So this problem, let's see what they're asking. So below they give us a sketch of the graph y equals the square root of x. So we can see that that sort of makes sense because if we go to the x coordinate of 1, we would expect, the square root of 1 to be 1. So 1, 1 should be a point on the graph. That makes sense. Square root of 4 should be 2. So 4, 2 is on the graph. Then we have 9, 3, and 16, 4. So that makes sense that this is what's called the toolkit function, or the basic function as they describe it, y equals square root of x. Our goal is to transform it into this equation, or this function. Now, there's a series of transformations that are performed here, and our job is to basically sketch the graph that is represented by this new function using what we've learned about the transformation logic. So here, what I want to start with is basically just kind of talking about the different kinds of transformations that are being done. So the first transformation that we see here is that we are basically scaling the x coordinate. Now, with scaling the x coordinate, you have to keep in mind that when dealing with the x in general, you have to keep in mind that whatever transformation you do, it's actually the opposite of what you think, because the x is the input to the function, so you actually have to do the opposite of the transformation to give it the same output value. I know that might be a little abstract, but it's not worth getting into that detail here. That's just what's required. So we have basically scaling the x coordinate. That's what this 1/2 means. Instead of actually compressing the x coordinate by half, or basically multiplying all the x coordinates by half, we're actually going to end up multiplying everything by 2. So we're actually going to end up stretching it out. Here, you see that we have a left shift, not a right shift. Normally, you would think that because it's positive 5, we would actually move to the right. But remember, with the x, everything is the opposite. So it's actually shifting to the left. So that's what's represented here. Now, obviously, the square root, that just represents the base function. So that's not actually a transformation. The next transformation that happens after that is due to this. This, when we're dealing with the y coordinate, which is outside of the x coordinate, outside of the basic function, which would be the square root in this case, then things actually behave as you would expect. So here, what we're going to end up doing is stretching the y coordinate. So every time we have a y coordinate, like like the coordinate 1, 1 here, it's going to basically be multiplied by 3. So it's going to be transported up here. This will be transported up here to 6, and then everything will be scaled up by 3, as you would expect. And then the final transformation, the last thing that we should do, is basically left shift by 8. So here you can see we have a -8, and because we're dealing with the y coordinate now on the outside, it does behave as you would expect. We basically shift it down because negative represents moving down. So those are the basic transformations. Let's actually try to take a couple points and basically go point by point and do this transformation. So um, let's see here. So let's first deal with let's deal with the origin, because the origin is a valid point in this function if x equals 0, y equals 0. First, we're going to multiply the x coordinate by 2 because we see 1/2 here and we need to take the reciprocal of it. So we'll multiply that by 2. 0 times 2 is 0, so it'll stay where it is. Then we're going to left shift by 5. So we're going to go 1, 2, 3, 4, 5. Then we're going to scale by 3. Again, that's not going to scale it because 0 times 3 is still 0. And then we're going to move down by 8. So we're actually going to go way off the graph down here. It's going to look something like this. That's basically where the origin is mapped to. Now let's talk about another function. So let's do 1, 1. First, we're going to multiply the x coordinate by 2. So now we're going to be at 2, 1. Then we're going to do a left shift, and we'll end up at -3. Then we're going to multiply by 3. So 1, 2, 3. And then we're going to subtract. And so now we're actually at the coordinate -3, 4. And then we're going to subtract 8. So we should end up at the coordinate -3, -4. So down 1, 2, 3, 4 to get to the origin, and then 1, 2, 3, 4 to get down here. So this is basically where the point A is mapped to, if you want to think of it like that. And then, just going through for a couple of these other ones, I'll just do one more and we can probably connect it after that. So here we're looking at the point 4, 2. So first we're going to stretch out the x-coordinate to 8. So we're going to go from 4 to 8 on the x-coordinate, which is here. And then we're going to subtract 5. So 8 minus, or sorry, yeah, 8 minus 5 will put us at 3. So now we're here after the second transformation. Then we are going to multiply this coordinate. Now we're going to start multiplying. So the x-coordinate is going to be here, is one way you can think of it. The x-coordinate and the y-coordinates are independent. Next, we're going to focus on the y-coordinate, and we're going to transform it. So basically right now it is, what is it right now? It is 2. So we're going to multiply by 3. So now it's going to be 6. And then we're going to subtract 8 to ultimately end up at -2. So if we just sort of connect, we've only done 3 dots here, but I think you sort of get the idea. If we connect it, it'll look something like this. This will be roughly what our sketch looks like. I don't know if I got the x-intercept right, but and also it starts here because the domain for the square root function has to be basically 0 or greater. You can't plug in negative numbers to the square root because that would be a complex number, which is something you're supposed to ignore at this stage. So this is sort of what we do. We're stretching it in the x direction, we're shifting it around, we're scaling it in the y direction, we're doing a bunch of stuff to it. We're basically doing every single transformation. And just before we leave, I'd like to type this equation into Desmos just to verify, which is a good online graphing calculator, if you're not familiar with that, just to verify that it behaves as expected. So go to Desmos, and then obviously we're going to do f of x equals x, or I'll say square root of x. So that's the normal one. That's what we expect. And then we're going to see how close we got on our sketch. We'll say g of x equals 3 f of, or whoops, f of 1/2, and then it should be x plus 5, if we're looking at it correctly. So yes, yeah, so 1/2 x plus 5, and then minus 8. So that roughly looks like what we drew. You see, we expect the, I forget what the actual origin was mapped to down here, but it's basically down here. You see it eventually intercepts the x-axis about where we drew it. So yeah, I drew it at about 9, so that's actually relatively close. And you can see it's sort of under the original one. So that just gives us a good verification that we actually did it correctly. So that's good. So we've taken care of step 1 in this problem. What we've basically done at this point is we've basically sketched the graph. So that's fine. We sketched the graph. Now what they're asking for down here is to find the new coordinates of the point D, specifically just the y-coordinate. Now, what we could do is we could sort of ignore the x-coordinate because, as I mentioned before, the x and y-coordinate are actually distinct from one another. They're not dependent on one another. The x-coordinate transformations, they can be applied without even thinking about y and vice versa. But I think it's actually a good idea to map this out specifically. So first, what we're going to do is we need to understand, in the same way that the origin is mapped to this point, and then point A is mapped here, point B is mapped here. We actually didn't draw where D is mapped. If I had to guess, it'd be somewhere around here, but I don't know for sure. I don't know the exact numbers. So the first thing we need to do is come up with some procedure to do that. So the first thing is that we're actually going to write down what D old is. I'm going to call it D old equals, what should we call it? So basically on this graph, it's 16 and 4. So that satisfies the equation. So the original point that we're working with is 16 and 4. And we want to understand what D new is. Basically, we want to understand the x, or the x and y coordinate after it goes through these 4 transformations from this base function. So what we can do is we can basically treat the x and the y independently. So I'm gonna treat the x with the color red. So the first thing that we do to our x-coordinate is we basically take whatever is in here inside the base. So whenever you see the base function or the basic function or the toolkit function, whatever you want to call it, you have the x up here. You're going to be replacing it with something more complicated in the transform function usually if you're doing an x transformation. So here we're actually looking at 1/2 x plus 5. What we need to do is we need to make sure that whatever is in here is actually equal to this old x. So the way that would work is we would say 1/2 times x, I'm going to call it new. That's going to be basically the new coordinate for D, the new x coordinate at least. And then we'll have plus 5. And and we're going to say that's equal to x old. So the reason that the equation is set up in this way is because we're talking about the input. So basically, whatever we end up with here ultimately has to map to the old coordinate in order for it to give the same output. So what we'll do is we will plug in the numbers. So like this, for example, is x old. This is what we're starting with. So this is the x coordinate of the old D point. So that should be 16. And then we're trying to solve for x new, by the way. So we have an equation of one variable in one unknown, or sorry, one unknown that we in one equation, which means we can solve it. So what we'll do is we'll multiply both sides by 2, and then we'll subtract by 5. So x new should equal, after multiplying by 2, it'll be 32, and then subtract 5, whatever that is. It looks like we get x new is 27. So x new equals 27. So we're looking at D. I thought it would be mapped here, but it turns out it looks like it's actually mapped out way over here. So it's actually gonna, D is actually gonna end up over here. Now the second thing that we can do, there are actually two options here. One option is easier than the other though. So the first option that we can do after we know x new, and remember I can write this up top here since we now know that. I'm gonna say, so that we know that the new x coordinate is 27. There are two options that we can do. We can either take this this new coordinate, and plug it into this complicated function, but that's actually a bit of extra work that we don't need, because we can take advantage of the fact that if you plug in x of 27 down here, you actually get the same output that you would have gotten if you just plug in 16 in the original function. And the output there is 4. So what we can do instead is we can just take this 4 here, which is the old y coordinate, and we can apply the y transformations just to that. So this is how that would look. Basically, the equation is going to be slightly different because we're now dealing with the outputs instead of inputs, but honestly, this is easier. That dealing with the outputs makes more sense, I think. So what here we're going to have is we're going to have 3 times what's y old, and then because we're basically multiplying by 3 on the outside here, which is a shift, it's a stretch in the y coordinate, and then we're going to subtract this 8 here. So subtract that 8, and we're going to say this is equal to y new, the new y coordinate that we're trying to find. Now what is y old, you might ask? Well, it's actually this 4 up here that we started with, so this is actually y old. So what we'll do is all we have to do basically is plug in 4 for y old into this equation, and then we'll solve for y new. So basically 3 times 4 minus 8 equals y new. So that should be 12 minus 8, basically y new equals 4. So that's interesting. It's actually the same as the old one, just by coincidence. So here we're looking at the new coordinate of 27 and 4. So basically the D is going to be, right now it's at 16, 4. Basically it's going to be shifted way over here. It's going to be the same y coordinate, but a much further away x coordinate. So this is our answer, actually. This is the new point D after it goes through this transformation, and the question is only asking for the new y coordinate, so the answer there is 4. We could have actually skipped this initial part and just done that, but that's basically how you work this problem. And in following videos, we're going to do some more examples just like this.